Ever wondered how DNA fingerprinting works? It's a fascinating technology that has revolutionized fields like criminal justice, paternity testing, and genetic research. At its core, DNA fingerprinting is a method used to distinguish between individuals of the same species using only samples of their DNA. One key component of this process is the PCR amplification of short tandem repeats, or STRs. These are tiny regions of DNA where a specific sequence of base pairs is repeated numerous times. By amplifying these STRs, we can create numerous copies of a particular variable region, forming the basis of detection. The process starts with a small synthetic piece of DNA known as a primer. This primer is designed to attach to a non-variable region of DNA that flanks the variable region. Once attached, the primer allows for the amplification of the STRs, providing us with the unique DNA fingerprint. Now that we know what DNA fingerprinting is, let's dive into the process of PCR amplification of STRs. So, how does PCR amplification of STRs work? Let's delve into this fascinating process. Imagine a short synthetic DNA, known as primers. These primers are not just any random sequence of DNA. They're specially designed with a purpose. They have a mission to attach to a highly conserved, non-variable region of DNA that flanks the variable region of the DNA. Think of these primers as the anchors that help us zero in on the exact region of DNA we want to study. Now comes the real magic. Once these primers are in place, we can begin the amplification process. By using a technique known as polymerase chain reaction, or PCR, we can create thousands upon thousands of copies of a particular variable region of DNA. This mass replication forms the basis of detection, but we're not done yet. After amplification, these copies need to be separated. This is where gel-electrophoresis comes into play. By running the amplified DNA through a gel, we can separate the STRs based on their size. The smaller the STR, the further it travels through the gel. By comparing the distance migrated by each STR, we can examine and measure them. This gives us valuable information about the STR sequence size, which can then be compared with other known samples. This comparison forms the final result of the DNA fingerprinting. The amplified STRs are then ready for examination. So, that's how PCR amplification of STRs works. A journey from primer design through amplification to gel-electrophoresis. What happens after the STRs are amplified, you may ask? Well, we delve into an intriguing process of analysis. The amplified STRs, each marked by a known repeat sequence, are separated using a technique called gel-electrophoresis. Picture this, a molecular race where the STRs are the runners. Now, each STR doesn't run the same distance. The distance each STR migrates is carefully examined. And why is this so important? Because this distance is a telltale sign of the STR's size. It's like a puzzle, and each piece brings us closer to the full picture. The STR sequence size amplified by PCR is compared with other known samples. This comparison, this matching of puzzle pieces, provides us the final result of DNA fingerprinting. And voila, we've unlocked a genetic signature, a unique identifier, if you will. That's how, through PCR amplification of STRs, DNA fingerprinting is achieved. Like any procedure, PCR amplification of STRs has its advantages and limitations. On one hand, the method is less costly, needs only a small amount of specimen, and takes less time to complete. However, it's not all rosy. It's less accurate than RFLP, and there's a risk of amplification contamination, which could distort results. So it's a bit of a balancing act. But here's the thing. Despite its limitations, PCR amplification of STRs continues to play a pivotal role in DNA fingerprinting.